Whoops. And I'm going to draw the inner circle, and S is the center. And it touches the sides at P, Q, and R. So I'm going to have to rename these. And then QR and BC intersect at M. Right. So that's the point that's in harmonic conjugation. So BPC and M are in harmonic conjugation. A circle passes through B and C and is tangent to the inner circle at N. Oh, this looks a lot like IMO, the problem that Irajan said earlier, IMO 2002 G7C. So a circle passes through B and C and is tangent to the inner circle. I think we might be able to just cite that problem. No, it's not BBC that's tangent, but yeah, I'm trying to remember let's see. Oh, now I remember how I got it. So if you draw the altitude, and then you take the midpoint of the altitude. I don't think it always lies on QR, but basically, if you let PE intersect a circle at a point, then I think BFC is tangent to the inner circle. Yeah. So here I'm using the problem that I think it was Irajan mentioned. Yeah, they're all just IMO shortlist 2002 G7, right? It's silly. So it's tangent at N. Yeah, certain countries like using ideas a lot. Like I think Iran really likes using Poncelet's porism. Like sometimes you'll just see the same themes come up over and over. The circumcircle of MNP intersects AP at L. And we want to show S, L, and M are collinear. I think maybe it's trivial from IMO shortlist. Yeah, it might be the same proposer. Yeah. Let's see. Is it obvious? So I'm gonna let's see. I mean, basically we want to show that SF is perpendicular to AP. So I'm going to change F to L just to match the problem. Let me hide a couple lines and then I'll look at the comment. But let's see. Whoops, just to make things look nicer. Whoops. There we go. Have I ever proposed a GEO problem? I have not. I have, there's a few ones that I've come up with myself, not a lot, but I've never proposed one, but maybe someday I will. So yeah. Let's see. Whoops. Is that actually necessarily true that SM is perpendicular to AP? I think it is. Yeah. We have to prove it. Yep. I'm not even sure how to propose an IMO problem, but I could always try. Let's see. Maybe this isn't as easy. So is it obvious first that MP is the diameter? So let's see. Oh, I forgot to draw the altitude. Yeah, so E is the midpoint of AD using IMO shortlist 2002. Let's see. So SNPM is a kite, right? Or no? Yeah, maybe this is harder than I thought. I thought maybe 2002 would trivialize this, but maybe not. So yeah, we want to show that. So yeah, let's see if we can show MP as a diameter. Is that even true? I think it's true. Yeah. Let's see. So angle B, we want to find angle BNP. We want to show it's 90 degrees. To find the midpoint of MP. Yeah, I mean, basically, I'd want to show that that's the center, right? I don't know that that's the center of the circle, but I think I have an idea actually. So I think it's not. I think I show in my video in 2002 that NP is the angle bisector of BNC. And so if that's true, since M is the point that's in harmonic conjugation, then MNP has to be 90 degrees. So MNP is a diameter and MLP is 90 degrees. Exactly. Yeah, MP. MPBC is -1, and so this, if you look at my video, I show that NP is the angle bisector of BNC in my video, and so that means, yeah, MP is the diameter of that circle, and so MLP is 90 degrees. Oh, but if that's true, yeah, how do we show SLP is also 90 degrees? Is ML, yeah, so I can prove that. That's what I just mentioned. So yeah, I figured out how to prove ML is perpendicular to AP. Now I'm just trying to show that SL is perpendicular to AP. Or MS is perpendicular to AP. So that's the same as saying that M. Oh, but we know MS is perpendicular to AP. Yeah, I think the problem is solved. Yeah, because since M lies on the polar of, yeah, exactly. M lies on the polar of A, so A lies on the polar of M. And so I think that should solve it. We have MS is perpendicular to AP and also ML, and we know ML is perpendicular. Yeah. So yeah, I'm referring back to my video on I'm a shortlist, but I think I show that the bisector of BNC, that NP is the angle bisector of BNC. So I'm just going to refer back to what I did in that video. Okay. So what video number? You said it was, I'm looking back, 34. Let me shrink the diagram a little bit just to make room. That's not easy to shrink the diagram. Did I even need that? I didn't even really need point E, to be honest. I needed it to construct the figure, but not to solve the problem. Oh well, my diagram will just get in the way of some stuff, but so NP bisects angle BNC. So I proved that in that video. Let me add a couple, all right? And so, but also B, C, P, and M are in harmonic conjugation. So I've mentioned this so many times, but I'll just write it out briefly. So AP, BQ, and CR concur by Cheva. So that means that BC, PM are in harmonic conjugation. And so if you combine these two facts, that means that angle MNP has to be 90 degrees. Okay. Which means that angle MLP is 90. And then once we know that, we can use the poles and polars. So M lies on the polar of A. So that means that A lies on the polar of M. So I'll write it like this. And if A lies on the polar of M, that means AS is perpendicular to AP. Or MS is perpendicular to AP. And so if we combine those two, if MS is perpendicular to AP and MLP is 90 degrees, then that means ML and S are collinear. All right, so I'm going to move on to the next one. So this is the last problem that I came up with, just because, oh, actually, maybe I have more. No, this is the last problem I've come up with just because I came up with more problems last night, but then my computer crashed, so I came up with them really quickly before this meeting. But maybe we can go search some problems together right after this, because usually I make it 3 hours. So we have a cyclic quadrilateral ABCD, and O is the circumcenter. All right. P is the intersection of AC and BD. So yeah, this one I think is pretty tricky. That's P. E is the intersection of AB and CD. Oh yeah, I'll try that problem after. So BMO, it's a problem from the Balkan Math Olympiad, right? So yeah, if we solve this one, then I'll do that one. So this is E. That's nice. It just showed E already. I is the in-center of EDC. Hold on a sec. I don't want to call it. I'll call it K. So see if this works. Oops. What's going on here? There we go. So that's I. The inner circle of EBC touches BC at P1. So call it T1. And the X center of EAD touches AD. Right, so let me draw some rays here. Hold on just a second. Okay, so this is the X center right here. And it touches AD at T2. All right, let's call that T2. Q is the intersection of IT1 and JT2. So this is J. So that intersection point is Q. And we want to show that OP and Q are collinear. That's pretty interesting. All right, let's hide some stuff. All right. So we have like a cyclic quadrilateral, and it creates like an N circle and an X circle. This feels like Ricard's theorem, doesn't it? So maybe I should let BC intersect AD at a point. Yeah. So I'm going to let BC intersect AD at G. And then OP is perpendicular to EG. So basically, we want to show PQ is also perpendicular to EG, right? That would solve it. So IT1 is perpendicular to BC, and JT2 is perpendicular to BD. That's interesting. So IT1 is perpendicular to GC, JT2 is perpendicular to GD, and we want to show that QP is perpendicular to GE. So we have like three, we would have like three perpendicular. So basically, we want to draw the circumcircle of GT1, T2, kind of. So if we draw the circumcircle of those 4 points, because those are both right angles, right? Then we want to show that QP and H are collinear. Yeah. Or that QO and H are collinear, either way. And also, yeah, E, I, and J are collinear. That's probably useful. see who's still on. Sec, I'll be right back. All right. All right, thanks for waiting. Let's see. How do we show this? Yeah, so we could think of Q as, trying to think of a natural way to think of Q. So it lies on the circumcircle of G, T1, T2. Yeah, we could, H is the intersection of EG with the circumcircle of G, T1, T2. And we want to show H, P, and Q are collinear. I wonder if we could use Picard's polar theorem again. Pascal's theorem. Possibly. I don't see an immediate way how to do it, but doesn't mean it's not possible. So we have GH, T1, T2, Q. Yeah, no, this does look like a hard problem. Maybe there's a different way of thinking about it. So O is the center of one circle. Is H the center of a different circle? Does HE equal HA? That seems like a coincidence, but I'll check it out. Yeah.
Oh, I had a nice case at cinema.
Oh, I'm sorry. Anmal, did you find something?
Not really till now.
Okay. let's see. So we want to show Q, P, and H are collinear. Or Q, O, and H. See, how do we, yeah, point Q is tricky. Yeah, maybe there's like some more natural way to think of point Q. It's the intersection of IT1 and JT2. Maybe we could use, this kind of reminds me of like orthologic triangles. So if you look at the triangles IJQ and B and GCD, you have the perpendicular from I to BC, the perpendicular from J to GD, and then yeah, but you don't really have the perpendicular from Q to CD. But let me try something. Can you show me how to do that? Or your idea for that? Let's see. Yeah, there's just so much information in this diagram, it looks hard. I'll do it for like another 15 minutes, but yeah, this is a tricky one. Yeah, it's weird because it's not like this is the end, it's not like this is the end circle and this is the X circle of the same triangle. They're, yeah, that makes it a little tricky. I wonder if IBAJ is cyclic. Yeah, IBAJ is cyclic and ICBJ is cyclic. Maybe that helps us. I think that might help quite a bit. I'm sure that's probably just an angle chase, right? I'm just going to draw one of them. So, yeah, that, because, let's see why that is. IBAJ, because angle IBE, we want to show that's equal to angle IJA. So suppose we know that IBAJ is cyclic. Is it even obvious that that's cyclic? Yeah, I think it's an angle chase because angle AJI is angle AJE, which is angle FAJ minus angle AEJ. Yeah, so it's an angle chase that IBAJ is cyclic and ICBJ is cyclic. So yeah, maybe there's like another way to use. I wonder if we let's try this. If we label these two intersection points K and L, oh no, EK and L are not necessarily linear. Is EK tangent? It almost looks true. Yeah, it looks like EK is tangent to that circle. That's really interesting. So I'm just finding out, look at you. I'm just finding random stuff here, but maybe it works. It is pretty funny. That's so random, right? I'm just trying stuff. All right. I don't know if that will help, but EK does look tangent to that circle that I figured out on accident. Let's see. Maybe. So that means that yeah, let me check it out. It's definitely tangent. We still want to show OP and Q are collinear. I'm trying to use Bricard's polar theorem. So let's see, what if we, is Q the center of some circle? I don't think QI is equal to QJ, but maybe. Oh, QI I think is equal to QJ. So that is I'm just finding random things, right? Isn't this what makes geometry so fun? QI is equal to QJ. And I think that's an angle chase. Yeah, because we can figure out the angle that QT2 makes with AJ, and we can figure out the angle it makes with AI. Yeah, so basically, I think that is pretty important. I'm going to delete this circle. It was pretty cool, but not sure if it's going to get me too far. So basically, we have O and Q are basically the centers of two circles. So Q is the center of a circle through I and J, right? So we want to show that the line between the centers of two circles, like that's always perpendicular to their radical axis. Maybe, like we want to show H, like is EG the radical axis of those two circles? How do you figure out, let's see. I guess one way I could figure it out. Yeah, how do you get the radical axis of two circles that don't overlap? I guess I could try this. So basically, if I draw the tangents from H to each of the two circles, no, I don't think that is the radical axis, because this tangent is longer than this tangent. Yeah. Why is it enough to show QP is perpendicular? So that's Bricard's theorem. So I think it's video 76 on my channel, but we can show OP is perpendicular to GE. So Bricard's theorem says if ABCD is like any cyclic quadrilateral, and O is the circumcenter, well, yeah, if ABCD is any cyclic quadrilateral and O is the circumcenter, and we have P is like the intersection of the diagonals, and then we define G and E like as the intersection of the sides like this, then GE is the polar of P. That's what Bricard's theorem says. So OP is perpendicular to GE by Bricard's theorem. That's why it's enough to show that QP is perpendicular to GE. Yes. And we have QI equals QJ, and IBAJ is cyclic, and ICBJ is cyclic. So well, hold on a sec. I think I might. Yeah, the fact that QI equals QJ has to be used somewhere, I feel like. So Q is on the perpendicular bisector of IJ.
Isn't X the Michael point of ABCD?
Or is what the midpoint of ABCD?
Michael point X of ABCD means that EBHC is cyclic.
The Michael point. So it's like, I think it's like is the Michael point like the intercept?
Yes.
Yeah, H is the Meckel point.
And because H is the Meckel point of a cyclic quadrilateral, hence HPO are collinear.
OP
It's
and
a H are collinear.
HO and P are collinear. I agree with that.
Yes.
Yeah, that's, and you can also prove that with Ricard's theorem. But yeah, either way it works. Yeah.
We need to prove that GQ is diameter of this circle GHQ.
Yeah.
Or basically we need to prove that GC perpendicular to EJ. No, wait.
Well,
GC perpendicular to IQ.
GC is perpendicular to
IQ.
IQ. We know GC is perpendicular to IQ.
I think we are done here then.
Oh, really? Okay.
Angle GT1Q
Mm-hmm.
is 90° means that angle GHQ is 90°.
Yes, I agree with that.
And so HQ is the perpendicular of GE. And we also know that HPO is the perpendicular on GE by Meckel point theorem.
So hold on a sec. That almost seemed too easy. Let me I feel like I see what you're saying. Hold on just a sec. So we know that OP passes through H. We want to show that QP passes through H. So you were saying, wait, how do you know that QP and H are collinear? Say that one more time. I think something might be missing. Say that one more time.
Sir, give me a second.
What?
Yeah, so once we know that HQ is perpendicular to GH,
Wait, but
then
we
also
don't. But okay. So how do we know HQ? Okay, so we know HQ is perpendicular to GH, and we also know that OP is perpendicular. I think I see what you're saying. So, but how do we know? Like, I guess it depends how we define H. Is H the intersection of this circle GT1 T2Q with EG, or is H the Meckel point? Yeah, basically, there's two different ways to define H, and we have to show that they're the same, basically.
I think we can prove that H is also the Meckel point of A, B, T1, T2.
A, B, T1, T2?
Yeah.
So, let's see.
We need to prove one of GABH cyclic. That would solve the problem. I mean that we are done with the part involving Q.
Okay, so basically we want to show GABH is cyclic, and that would solve it, right?
Yeah.
All right.
Yeah.
Okay.
I think we can go power of point here.
We can use power of a point.
Maybe.
So like we could show EH times EG is EB times EA.
Let me just give me a second. Let me solve on some pen and paper.
Okay. This is interesting. Yeah, so yeah, do we even need point Q? But basically, we just want to show that H is the McKell point of ABCD. So, and T1 and T2, we don't even really need point Q. Yeah. Interesting. Yeah, it looks like power of a point. So, but ET1, yeah, let me move things around a little bit. So, yeah, it's tricky to do it with power of a point. I mean, yeah, we want to show E has the same power with respect to those two circles.
Can we instead try proving that the Mikkel point and G, T1, T2 are cyclic?
Yeah,
I mean,
that is
define
another.
Mikkel point.
Yeah, we could do it that way too. So if you take the McKell point, for example, then we want to show that GH, T1, T2, Q are cyclic. So H lies on the circumcircle of G, T1, T2, Q. We could do that too.
I think we are done with the point Q here. We can remove it from the figure.
Yeah, we can remove point
confusing.
Q. Yeah, we don't need point Q. Yeah. So yeah, it seems like yeah, it seems at least that should be easier to prove. Yeah, so that would be a lot of circles. Yeah, we get that's
Try inverting on H.
Inverting on
Lot
H.
of circles.
All right,
The
so
4 circles there means we can try to invert.
all right, before I try inversion, let me see if there's a quicker way to do it.
There should exist a better solution though.
A what?
I mean, inversion doesn't seem necessary here.
Yeah, there's. So yeah, we want to show angle HT1E is this angle.
Isn't it like that EBC similar to EDA and EI is just the midline, so we can reflect ECB
We can
along EJ.
we can reflect EBC along EJ, and then
Yeah, that would make BC parallel to AD. We
yeah,
haven't basically used the fact that ABCD is cyclic, right? And that in center.
okay, so like yeah, so BC and AD are anti-parallel, right? So if you reflect it over the angle bisector, it's parallel to the other, right? I get that. Do you see how that solves it, or you're just sort of thinking? Let's see. So yeah, we want to show GHT1, T2 is cyclic, right? Yeah, let's see. Yeah, there's so many cyclic quadrilaterals: GHAB, GHCD, HBEC is cyclic. Is that all of them? I think EHAD is cyclic. Yeah. Any 4 points are cyclic. And we want to show GH. Isn't that a pretty picture? And not only that, these are cyclic and these are cyclic. Isn't that fun? And then also, I'm not going to draw any more cyclic quadrilaterals than that. All right, so we want to show GH.
There was something like called sliding lemma. I forgot what it was exactly.
Okay. Yeah, let me know if you can remember it or if you can find it on the internet. Yeah, but you think inversion at about H would work? I don't know. Let's see. So we want to show angle. Yeah, so BC and AD are anti-parallel. Let me try something. But hold on, if we reflect, I think if we reflect T1 across the midpoint of BC, or we could do the same with AD, but like if we take the midpoint of AD, so you're reflecting ABCD over O. Oh, that was your original idea. Like find all the so okay. Yeah, I wonder, let me try this. Are C, B, and H collinear? I don't think so, but maybe. Wait a sec. I would be very surprised if that were the case. Yeah, no. So you were trying to use Pascal that way. That's interesting. But yeah, it seems like showing GH, T1, and T2 are cyclic is a simpler problem than the original. It seems like that's the way to go. I'm just not sure. All right, sounds good. See you later, John. Have a good one. All right. So how would we show GH, T1, T2? Just trying to think if there's like a nice way to think about that. So yeah, we have like a point G and the two tangents to two circles. Yeah, we want to show T1, T2, angle T1, T2H is equal to angle T1, GH. But yeah, like what I was thinking is like, yeah, like I want to, like you mentioned, like using the fact that they're anti-parallel. So I think that could help. Let's see. Yeah, I'm just going to stick with this problem until 1 p.m. or until for the next 20 minutes. Let's see if we can do it.
Because EBC and EAD are similar, we know that BT1 by T1C is equal to AT2 by T2D. Does that help?
Yeah. So BT1 over T1C is equal to T2D. I'm sorry, AT2 over T2D. Yeah. So they're in the same ratio basically. Wait, does that mean ET1 and wait? Oh yeah, not necessarily. But yeah, they're in the same ratio. And then is it just power of, let's see. Let me check something. So Yeah, that seems, I think the power ratio lemma might finish it off because we know GABH is cyclic, and we know GDCH is cyclic. And T1 and T2 are like the same ratio of the distance from B to C. So I think the power ratio lemma finishes it. Because basically, since if you look at the have you heard of the power ratio lemma? Basically, we have these two circles through G and H, right? GABH and GDCH. And if you look at the points T1 and T2, you can take the ratio of their powers with respect to both circles. So, and it's the same for T1 and T2. And if that's true, then that means GH, T1, T2 is cyclic. So that solves the problem. So I think I did the power ratio lemma. It's a previous video on my channel. Let me see what number it is. But I'm going to check out the number. Let's see. So let's see. It's video 68. So if you look at video 68 on my channel and the power ratio lemma, you can apply that and it shows that GH, T1, T2 is cyclic. So I'm going to write this up. But that solves it. All right. So maybe I'll just give a sneak peek at one more problem just because we were able to. Well, probably most of my time is going to spend typing this up, but all right. So let me start from the beginning. Let's see. I don't need. Let me unhide a couple things. Yeah, I'm gonna add this back in, but okay. So basically, this is the original problem, right? But I don't know yet that that's circle, but I didn't even use it. Okay, so the circumcircles of ABG and CDG concur at the Meckel point of quadrilateral ABCD, which lies on EG. So does it only lie on EG because they're cyclic, because ABCD is cyclic? I think it would lie on EG anyways, but it's part of the theory. Okay, so I'm going to draw those two circles. And then OP and H are collinear. I'll say by Bricard's polar theorem. OP passes through H. Okay. Now I'm going to show that GH T1 T2 is cyclic. So since BC is anti-parallel to AB, yeah, there's a lot of well-known facts used in this proof, but yeah, BT1 over T1C is equal to AT2 over T2D. So yeah, I'm just gonna, just for the YouTube viewers, I'll just explain it like this. So CX the of the EX circle. Okay, so I haven't drawn X, but that would be true. And then I'll just say, yeah, we don't even need the ratio. So I'll just say it like this, actually. I'll say BT1 equals CX and CT1 equals BX. Okay. And then BC is anti-parallel to AB with respect. So that means that BT1 over CT1 is equal to BX, or CX over BX, which is equal to AT2 over T2D. Okay. And then, so All right, I like this. So the power, if we take the ratio of the power of T1 with respect to the circle GBA, divided by the power of T1 with respect to GCD, that's equal to T1B times TG over T1C times TG. Which is, or maybe I'll write this, just make it the same as the previous equation. BT1, I'll write this as CT1. All right. And so similarly, we have the same expression with T2, so I'm just going to copy paste. Let's just take out the middle. Let's see. That would be AT2 over CT over DT2. Okay. Yeah, I'm just gonna. So I forgot, what video did I say that was? So the power ratio lemma says GH T1 and T2 are cyclic. I forgot what video I just said that was on. But yeah, let me check for a sec. That's video 68. Okay, so by the power ratio lemma, that means that GH T1 T2 is cyclic. Yeah, I'll just write, so yeah, that's equal to BT1 over CT1. Yeah, so since those two powers are, since the ratio of the powers are equal, GH T1 T2 is cyclic. And also, we have angle GT1Q equals angle GT2Q equals 90. So that means that GH T1T2Q is cyclic. All right. And if that's true, then that means that angle QHG equals 90. And that means that QO, P, and H are collinear. All right. So that is the last problem we will do. Let me see if there's a way to make this text like so that it just has like a white background. I think there's probably a way to do it, but I'll look at that for next time. But does this make sense, Animal? Thanks for your help on this problem. All right, so with that, I am going to finish the session now, but thanks everyone for participating. This was definitely a lot of fun. See you next time.